Hi, welcome back. We're in lecture 15 and the topic is t-tests. And in this segment we'll cover independent t-tests. As we reviewed in the first segment, an independent t-test is appropriate when you want to compare two independent samples. So two completely different groups of people or entities. It doesn't have to be people. So common examples, you might want to compare men and women on some measure. But also in experimental research, this is where you would compare, say, a treatment group and a control group. Or in medical research where you would compare patients and healthy controls, and on and on. This is one of the most common statistical tests that you'll encounter. So the example I'm going to use to illustrate this is, again, the working memory training example because we're so familiar with it, and also to let you in on a little bit of the details of this research that I left out when I first talked about this example back in the beginning. And that is, in the original working memory training experiment that I described at the beginning of the course when we talked about experimental research, they didn't just have a training group and a control group. The researchers actually had 4 different training groups, independent groups, that trained for different amounts of time. So some people came to the lab and they were randomly assigned to train for 8 days, some for 12, some for 17, some for 19. And those were independent groups of subjects. So we could do pairwise comparisons via independent t-tests. And to give you a preview, this is what the data look like. And if you remember back at the beginning, I was a little bit skeptical about the working memory training effects and whether that particular study was a very strong study. I left out this piece, and I'm bringing it back in to sort of be fair to the authors of that study. Of course, they probably watched that first lecture and then tuned out. They won't make it here to lecture 15 or whatever we're on. But this effect was very interesting in their work because it showed that the gain scores, that is the difference between intelligence post-training and intelligence pre-training, was a perfect linear function of amount of training. So that made their training effects a little more convincing. Again, remember back to the first lecture, there were a lot of other problems, potential confounds, but it was this result in particular that made me a little less skeptical. So I wanted to bring it back. And it's a good example to illustrate these independent t-tests. So what we could do here is we could compare, say, like between 8 days and 12 days. Is that a significant jump? It doesn't really look like it, right? From, say, 8 to 19, that looks like a significant jump, clearly. But where are the significant jumps happening? We can do that by doing all these t-tests. And again, just like we did with the dependent t, we're going to do a thorough analysis. We're going to get a t-value, a p-value, Cohen's d for effect size, and we'll get interval estimates. So again, the t-value is just an observed value minus an expected over standard error. The expected difference between the two groups under the null hypothesis is 0. So again, that falls out of the equation. So it's simply what we observed, the difference between mean 1 and mean 2, that's here, relative to what we would expect due to chance. And that's standard error. But here it's standard error of the mean differences. So the formula is a little different down here. It's standard error for group 1 plus standard error for group 2 divided by 2. So it's slightly different math, same exact concept as the dependent t. That t-value is also going to yield a p-value, just as it's done in all cases prior to this. It's going to be based on the actual t-value and the t-distribution, which depends on sample size and whether you're doing directional or non-directional tests. Remember, the NHST is biased by sample size, so we're also going to include an estimate of effect size. When comparing means, the most common estimate of effect size is Cohen's d, and here it's just the mean of group 1 minus the mean of group 2 over the pooled standard deviation. What do I mean by that? This is a little different from the dependent. We have two separate groups here, right? So we have to pool their variances or their standard deviations. So the pooled standard deviation is just the average of the two groups. So get the standard deviation for group 1 plus group 2, divide by 2. And again, we can do interval estimates just as we've done before. We get the sample mean. We can do this for both samples. Get the upper bound by adding some function of standard error. Same exact procedure as we've done several times down. There's one extra step, though, in doing an independent t-test. And this previews where we're going in the next lecture and the next set of topics on analysis of variance. And this is a really important assumption underlying independent t and underlying analysis of variance. The assumption is this. It's called homogeneity of variance. That sounds sort of technical and weird. All that means is we're assuming that in these two groups, there's an equivalent amount of variance. Why are we making that assumption? Well, just go back a couple slides and look at the math. We pooled the standard deviations from group 1 and group 2, and then we got a standard error estimate based on that pooled standard deviation. So if we don't have equivalent variances across groups, it's not really fair to just pool them that way to get our standard error estimate. Our standard error will be invalid, and therefore our sampling distribution will be invalid, and our p-value will be invalid, and so on. So we have to test that and see if the variances are different across groups. So how do we test it? How do we detect whether we violated this assumption? We can just conduct what's called Levene's test. And Levene's test is essentially like a t-test, but instead of comparing means, it's comparing variances. So if it's significant, then you've violated the homogeneity of variance assumption. So if that happens, what do we do? Well, first of all, and this is a lesson I always try to convey, not so much at the undergraduate level, but with my graduate students who are doing actual research and working on their own data. When you violate an assumption underlying a statistical test, don't freak out. It doesn't mean that the data are bad and you have to scrap the whole thing. It might be telling you something very interesting, right? It's an effect in your data. So just like we're looking for significant differences in means, it's telling you you have a significant difference in variances. That might be important. So when you get some violations, and we're going to be doing a lot more of these kinds of tests of assumptions as we go into analysis of variance, don't ever take it as a bad thing or as a negative or like, oh darn, I have to scrap the analysis. No, it's interesting. It's telling you something very interesting about your data. That's the way to sort of to handle it. But procedurally, what do you do? Well, there's a simple procedure that we're going to do in lab called Welch's procedure, where we're just going to adjust the degrees of freedom and the p-value so that we can protect ourselves against this increased probability of type 1 error that's often associated with violations of homogeneity of variance. Or you could take a radically different approach. Rather than do a t-test, which is called a parametric statistic, it's called parametric because we are trying to make inferences about population parameters based on this sample, right? The central limit theorem, going back to all of this has been parametric. You could just abandon this approach altogether and do a non-parametric test, and we're going to cover that at the end in the very last lecture, lecture 24. So let's get back to the example, working memory training. Remember, we had 4 different groups who trained for different amounts of time, and what we're looking at is their IQ gain. Here again is the graph, and what I'm going to present to you is our output for all these pairwise comparisons done as independent t-tests. Before I do that, here's the summary statistics. So this just shows you the means are going up as a function of training. You just saw that in the bar plot. But what I wanted to point out in this slide is here are the standard deviations across the 4 groups. They're pretty similar, right? So we're gonna conduct the Levene's test to make sure that we have homogeneity of variance, but just by eyeballing my summary statistics, I'm feeling pretty good about that. I think we're gonna be safe in terms of Levene, but we should do it. So here's the result of the Levene's test. Again, we're gonna cover this in the next lab, but there's a function in R called Levene test, where you just put in the dependent variable, tilde, independent variable, and it gives you a p-value, actually an F ratio and a p-value, and this one's really high, it's not significant, so we're safe. We can say, all right, we have homogeneity of variance, we can do the regular independent t-test. So here's the first one of a series. The first one I did was just 8 days of training versus 12 days of training. It's still the same function in R that we used for the dependent t-test. It's just t-test, t.test. And we just put in the 2 variables that we want to compare. But now, remember, in dependent, we had another argument that said paired equals true. The default in the t-test function is that paired equals false. So we don't have to touch it. You don't see that argument here. What we do have to add in, though, is var.equal equals true. What does that mean? That means we have homogeneity of variance. So we tested it, it's true, we have to throw that in. This is where the developers of R are a little bit snarky and clever. No one else would do that. What they're doing here is they're forcing you to test the homogeneity of variance assumption before doing this test. Otherwise, the default will be that var.equal is false. So the default is false. So I love it. It's a really nice feature of the package is if you don't test the homogeneity of variance assumption and you just run t-test with it without putting in that argument, you're essentially lying. So the developers of R are pretty clever with that. So let's now go into the output. Here's the t-value. Doesn't look very big, right? So there's the p-value, not significant. If you think back to the bar plot, it didn't look like a very big increase from 8 days to 12 days. So not a significant effect. So if they had just stopped at 12 days of training, they wouldn't have seen a significant effect. Degrees of freedom is 38. What that means is there were 20 students in each group because it's number of students in one group minus 1 plus number of subjects in another group minus 1. So 19 plus 19, 38. Again, what R does is it gives you an interval estimate around the mean difference. And as you can see here, this interval includes 0. That's why we have a non-significant effect. And then finally, we have Cohen's d, which is about 0.3, which is actually nothing to sneeze at. I've had results that I've published that were effect sizes of 0.3. How did I get them published? Well, I had bigger sample sizes, right? If I have a bigger sample size, an effect of 0.3 is going to be significant. So it's not significant here. P-value is 0.34. Now let's extend it out. Let's go from 8 days to 17 days. Now we're getting a significant effect. So now we got a t-value of 3.8. Again, think about those sampling distributions. That's way out in the tail, as indicated by the p-value. We have our interval estimate here. It doesn't include 0 anymore. And a nice, healthy effect size, Cohen's d, of 1.2. If you ever see a Cohen's d anywhere around 1, that's a big effect. Again, think about what it means. It's in standard deviation units. So these people changed a whole standard deviation. Just think about that for a moment. As a function of doing this working memory training, people increased a whole standard deviation in their IQ. That's pretty amazing. I don't know if I buy it, but that's the result. Okay, now let's look at 8 versus 19. Of course, this one's going to be significant too. I'm going to go through this quickly because it's all just the same format. Here's the t-value, low p-value, get an interval estimate, and nice healthy effect size. Let's look at 12 versus 17. Again, same story in 12 versus 17. Not quite as big of an effect, so we have t of 2.8. Still, though, really low p-value and an effect size that approaches 1. 12 versus 19, this is also going to give us a really strong effect. So t of 3.79, low p-value, again, nice effect size. This last one is a little different, right? Because these are the last two, 17 and 19. And here it turns out there's not a significant difference. So the t-value is 1.1, p of 0.26. So not a significant difference. Again, the interval estimate includes 0. That's evidence that it's not going to be significant. And Cohen's d, instead of being around 1, it's back down to about 0.3. So if we look back at the graph again, you could sort of see it in this bar plot, right? So what wasn't significant? Well, this comparison, right, that wasn't significant. And this comparison, that wasn't significant. But everything else was. So clearly, as you go from here to here, you have a significant increase. As you go from here to here, you have a significant increase, and likewise here. Okay? So that's an illustration of independent t-tests with 4 different groups. They were separate groups of subjects, so we could do independent t. But wait, wasn't that tedious? Like, there were a lot of slides there that looked exactly the same, right? And just by looking at the bar plot, we sort of could have figured out what we figured out by running all those analyses in R. So do we really want to conduct multiple t-tests like that? No. It's tedious. It could get worse, right? We only had 4 conditions there, or 4 groups. The other more serious problem is if you do multiple t-tests on the same set of data like we just did, then you're really increasing the chance of a type 1 error. So if we do multiple comparisons like that, then we have to build in some mechanism to protect ourselves against that increase in the probability of type 1 error. And again, we don't want to just do all those tests when it's just one experiment. Isn't there one procedure that does all this for us? Well, yes, indeed there is. It's called analysis of variance, and that's what we're going to cover in the next lecture.